This is an invited talk, and Alastair is going to be talking about the excuse me, the UK space industry's involvement in exploration missions. So, Alastair.
Thank you very much. Okay, fantastic. Okay, I'll keep an eye out. Hopefully I won't need either of them. Hi, my name's Alastair Wayman. I work at Airbus Defence and Space in the UK as a future programs engineer, and I wanted to take a little bit of time to tell you about the UK space industry's involvement in exploration missions. So I'm going to start with a small overview of the UK's involvement in space and exploration, then touch a little bit on our past involvement in exploration, look at what we're currently doing, and then focus mostly on the future. So the UK space programme mainly consists of contributions to ESA's missions. So the UK is one of 22 member states of the European Space Agency. What that allows us to do is to access the ESA budget, which is about $5.1 billion a year. Not all of this is on exploration, though. It's split between all the different disciplines, and there's about $560 million, give or take, per year for exploration. The UK's involvement is currently focused primarily on the Moon and Mars, and we've done quite a number of previous studies into those that I will touch on. So looking at the past, which I define as the things that are kind of currently in orbit at the minute, the UK had some involvement in the Rosetta mission, so we provided the propulsion structure and thermal subsystems for that. We also provided similar elements to the Venus Express mission and the Mars Express mission. For Mars Express, we also provided the Beagle 2 lander. Ultimately, this lander was unsuccessful. One of the solar panels didn't deploy, so it couldn't transmit back to the orbiting spacecraft. But what it did allow the UK to do was to learn a lot about the Martian surface and the Martian atmosphere. So now moving on to the present, so things that are kind of in development at the minute. When, with all the information and knowledge that we gained from Beagle 2, we applied that in the UK, and that allowed us to take a really leading role in the development of the ExoMars rover vehicle. So Airbus DS UK is the prime contractor for this. ExoMars itself is a two-mission program that's a collaboration between ESA and Russia. There's an orbiter and a descent demonstrator that's going to arrive at Mars in October. They've already been launched. And the rover vehicle will launch in 2020, arrive at Mars in 2021. Its mission is to search for biomarkers beneath the Martian surface. And to do that, it's going to have a 321 Sol nominal mission. And it'll have quite a sophisticated autonomous navigation system on board it that's going to allow it to traverse up to 100 meters per Sol and give it over that 321 Sol mission about 4 kilometers total travel. You can see in the video there at the bottom one of our Mars rover demonstrators that we're doing quite a lot of tests with in our Mars yard in Stevenage, just outside London. In terms of the payload, it's going to carry a drill so that it can collect samples from up to 2 meters below the surface, and there'll be a variety of external payloads that will allow it to identify suitable sampling locations and then characterize those before we take the samples. And then there's also going to be quite a sophisticated onboard sample analysis package as well. We're also involved in Prosper, which James talked about earlier on a little bit. So this is one of the ESA contributions to the Russian Lunar Research mission, going to launch in 2021 to the Lunar South Pole region. There's going to be samples collected, again, by a drill, and then Prosper is the sample analysis package for that. It's taken quite a lot of heritage from the Philae lander. And the development of this is led from the UK again by the Open University, but with contributions coming from RAL, also in the UK, and Airbus DS UK. Now looking further towards the future, but sticking initially with the lunar theme. This is another thing that James spoke about in his presentation earlier on, the Lunar Volatiles Prospector mission, which we've studied again in the UK. So this is a rover vehicle going to explore the permanently shaded regions of the lunar South Pole. It'll have a 1 to 2 year mission lifetime, and then periodically over that it will traverse into these permanently shaded regions, spend about 8 hours in the darkness at a time, collect samples from between 0.5 meter and 1 meter depth, and then analyze these again with an onboard sample analysis package. It'll also collect samples from slightly deeper when it's not in the permanently shaded regions, and be able to do some slightly more sophisticated analysis as it's got the additional power. This rover is planned to be teleoperated from Earth, and again, James touched on this previously, but we also performed some tests involving Tim Peake on teleoperation of Martian rovers, but also applicable to other rovers on the Moon, maybe. In our Mars yard in Stevenage. We've also performed quite a number of other field trials involving rovers. So under the frame of the SAFER program, we took one of our rover platforms out to the Atacama Desert in Chile and performed a mock Mars mission. So roving around the surface, identifying locations to sample, acquiring a sample in inverted commas, and then analyzing that. The rover was out in Chile, but the operations were performed in Oxford in the UK. We also performed the FASTER project, which involved looking at how a scout rover could be used to increase the rate at which a main rover could traverse across the surface by testing out different locations and identifying what the soil properties were and whether we could drive on those areas or not. Sticking with Mars, we've also studied, as I said, a couple of elements that would be useful for an eventual Mars sample return mission. So one of those is a Mars Precision Lander. It consists of a carrier module that would take the lander element all the way to Mars. There'd then be a 2.8 meter diameter aeroshell, and inside that there would be a 16.2 meter diameter disc gap band parachute. The dropship would then perform a powered descent using 14 high-thrust European thrusters. It'd have active hazard avoidance during the descent so that we could identify safe locations to land. And then, similar to the kind of sky crane idea, the rover would then be lowered from a 7.5 meter bridle down onto the surface. This system would give us a landing precision of around about 8 kilometers. So the payload that would deliver to the surface would be a sample fetch rover. Again, something that we've studied within the UK. This would collect cached Martian samples similar to those that are going to be cached on Mars 2020. It's a really low mass and very compact rover vehicle that has quite a large traverse, so that it can go to a large number of locations and collect quite a significant number of cached samples. Moving slightly further away from Mars now, but still in the Martian system, we've just finished studying to phase A level a mission to Mars, to Phobos, to acquire 100 grams of sample. So this is a candidate post-ExoMars mission that would allow us to understand a lot more about the formation of the Martian moons, and then also in several respects act as a demonstrator for a Mars sample return mission. So it'd launch in October 2025. We'd then acquire the sample from the surface of Phobos in 2028, and then that sample would be returned back to Earth in August 2030. As I said, we've studied this recently up to phase A level, and through that we've demonstrated the feasibility of the mission in terms of programmatics, the financial aspects, and also the technical aspects. The mission consists of a 4-module spacecraft. So the first module would be a propulsion module, which would carry us all the way to Phobos, and would have a European 1.1 kilonewton thrust bipropellant engine on board that would perform all the large delta V maneuvers. We'd then have a lander module on top of that that would carry the majority of the science payload and also the sampling system. perform a powered descent down to the surface before a free fall of around about 50 meters to limit the contamination. Once we've acquired the sample, this would remain on the Phobos surface. The Earth return vehicle would sit on top of this, and this is where the real intelligence of the mission lies. This is the thing that would control the composite all throughout the mission, and it would carry the Earth re-entry capsule all the way back to Earth after it's ascended from the surface. The Earth re-entry capsule then does pretty much what it says on the tin, contains the sample inside it, and allows it to re-enter into the atmosphere before a hard landing in Woomera, Australia. In support of the Phobos Sample Return Project, we've got quite a number of technology development activities that are underway in Europe that the UK is heavily involved in. So the first of those is the development of the landing gear system. It's a really crucial subsystem for the mission, as it's got to ensure the safety of the mission, both during the touchdown phases, but also during the on-surface sampling activity phases. It's being led by Senair, a company in Spain, but Airbus DS UK is providing some system-level support to that activity as well. Phase 1 is currently underway, where we're designing and simulating the landing gear, and Phase 2, where we're going to be performing reduced and full-scale testing in a reduced gravity environment, is going to begin towards the end of this year. In the UK, we're also leading a project called Sampler, which is designing, developing and testing the entire sampling chain for the Phobos sample return mission. And again, we're doing the tests in a reduced gravity environment. Phase 1 is where we've developed a dynamic simulator and then validated that through reduced scale tests. You can see the test setup on the right-hand side where we have a reduced scale lander. It's supported by a spherical air bearing in the middle, and then underneath that it's on a planar air bearing. The tests for those are completed, and fortunately they show quite benign dynamics, which is quite nice. Phase 2 for that, where we're going to be doing a full-scale test of the entire sampling chain, will be beginning again later on this year. I've got a quick video here just showing, is that going to work? Maybe that's not. No, yeah, if you could just run the video, thank you very much. No, is it going to work? No, does the video not work? Okay, fair enough. So essentially this was going to be a video of the test setup and just show you that not that much happens, but that we've done the reduced scale tests. Continuing with the theme of the sampling chain, this is a fully UK funded project. All of the other ones are European Space Agency funding, but this is a UK Space Agency funded project to develop a flight representative planetary robotic arm. The only difference between this and a flight arm is that the joint torques have been increased. The advantage of that is that it allows us to operate full-scale payloads with a representative arm in a 1G environment without any of the complications of gravity offloading. And so we can quite easily rehearse operations with scientists so that they can understand the capabilities of their instruments when mounted on a platform like this. Moving again slightly further away, so this time looking at asteroids, the UK's led the study of an asteroid sample return mission within Europe. So we spent about 8 years developing this mission. It consists of a single spacecraft with both a solar electric propulsion and a monopropellant propulsion system on board. It would aim to acquire 100 grams of sample from asteroid 2008 EV5. The way that it do this is it perform a touch and go sampling from the surface with a rotary brush sampling mechanism. This is a really low cost exploration mission that again has quite a lot of relevance to Mars sample return. The final thing that I want to talk to you about is our Europa Penetrator concept as well. So this is a concept that would be released from an orbiting spacecraft or potentially a flying spacecraft performing a flyby. It would then use the delivery system that you can see at the bottom to slow itself down before free falling down towards the surface and impacting at around about 300 meters per second. That would generate an impact shock of about 35,000 G, but it would allow itself to bury into the European surface by about 3 meters depth. Once it's done this, a sample would then be acquired by a drill that would poke out from the side, bring that back in, and then there's a mass spectrometer on board that would be able to perform some astrobiology. And then I do have a video, but are you able to run this video at all? Okay, I'll take that one as a no. And then let's try one final time. Are you able to run this video? Okay, if not, no? Okay, there you go. So what we also performed in the frame of this project was quite a number of full-scale tests where we took the penetrator, we attached it to a rocket sled in South Wales and fired it at a target of around about a ton of ice just to see what the impact dynamics were like. And you can see the video, the high-speed video here. It's quite dramatic. We also performed these tests into a similar size target of sand, as we were aware that, okay, Europa is the baseline target for this, but it's applicable to other targets as well, such as Mars, or potentially, as we were discussing yesterday, Phobos could be an applicable target as well. So thank you very much for listening, everybody. Hopefully that's given you a very brief overview of exploration-related activities within the UK, and I would welcome any questions.
Okay.
Good effort.
I kind of feel like it should be asked, but how will recent voting results in the UK have an impact on your space exploration plans?
We think that it'll have a very limited impact because the EU and ESA are completely separate entities. So there's quite a number of countries that are members of ESA that are not members of the EU. So we don't expect that leaving the EU will have an impact on that. Yeah, so this is the video that I wanted to show you. As you can see, not a huge amount happens, but that's a good thing when we're looking at the dynamics during sampling. You can see that as the sampling mechanism on the left-hand side comes down, then this front right leg lifts up. As I said, nothing too dramatic, but when you're sampling on the surface of Phobos, that's pretty much what you want. Yeah.
So you mentioned using the penetrator on ice and sand. Are there thoughts on ice that's with sand frozen in it as well?
I don't think we've specifically studied that at the minute. We certainly haven't done any tests on that. But in the future, if there's potential missions going to those locations, then yeah, I think it would be an applicable technology, definitely.
One last question, Derek. Derek, turn around. Yeah.
I've got a friend here to catch me. Yeah. Your target for the near-Earth asteroid sample return mission is the same target as OSIRIS-REx. Does it make sense to send two asteroids, missions to the same asteroid?
This mission was one that was previously being considered by ESA. It was a candidate for the M3 mission calls, where they've actually selected a different one. So as much as we've studied it, we spent 8 years studying it, a different mission has been selected. So that one at the minute is very much on the back shelf.
It just tells you that was an easy target.
Yeah.
Yeah, and just to clarify, I think that it's going to go for the Hakeem Olajuwon kind of. Anyway, it's not that it's the OSIRIS-REx target; it's the ARM target.
Oh, sorry. Yeah.
So.
Yeah.
Okay. Well,
Okay.
Alastair,
Thank you very much.
Again.
Thank you.
This ends the missions and international section. Thanks again to all of our speakers, and I'm turning it over to